technique, the method that we just learned to diagonalize a matrix, to diagonalize this matrix. And then once we have that, I want to show you why this is useful. I'll use the diagonalization to compute a high power of A, and even better, to get a formula for a to the n for any n, whether n is 1,000,000, whether it's 10, whether it's 5, whatever it is, I'll get a formula for it. Alright, so let's start. I want to diagonalize A. So we now know that to diagonalize A, you need to find a basis of eigenvectors for A. So I'm going to find the characteristic polynomial, find its eigenvalues, and then for each eigenvalue, find a basis for the eigenspace. Alright, so the characteristic polynomial is the determinant of A minus xi. So I'll end up computing this determinant here. I'll give you a second to stare at it and figure out how you would expand or do row operations or anything of the sort. I think you've seen it. The second row is especially nice. So I'm going to expand on this second row. That's plus, minus, plus. So the only entry I have will get a plus. So I have 1 minus x. Then I'll get a 2 by 2 determinant. So I'll have minus 1 minus x. 7 minus, 7. Minus 1. I'll have 0 minus 2 minus x. Alright, so this is especially nice because now I get a 2 by 2, which I always can do pretty quickly, but better than that, I'll have 1 minus x, minus 1 minus x, and minus 2 minus x. So in fact, my polynomial is already factored. Let's just write it nicely. I have x minus 1, x plus 1, x plus 2, so my eigenvalues will be 1, minus 1, and minus 2. I have 3 eigenvalues. Each one will have 1 eigenvectors, and so at this point, I can already say my matrix will be diagonalizable. Still need to find those eigenvectors though, so let's start with lambda equals 1. I want to look at A minus I. That's going to be the matrix minus 2, 7 minus 1. So 0, 0, 0, and 0, 15, minus 3. Alright, the eigenspace corresponding to lambda equals 1 will be the null space of this matrix, so I should reduce it. I have it reduced in my notes. I get 1, 0, 0, 1, and then I have minus a fifth. Alright, so for this I've used magic. And you can see you have a free variable in the third column. So let's say this is s. I'll have x equals 1/5 s, y equals 1/5 s, and z equals s. So this would give me 1/5, 1/5, 1 times s. And so that's going to be my basis for this eigenspace. So my basis for the eigenspace of 1 will be 1/5, 1/5, 1. All right, 1 down, 2 to go. I've done 1. I need to do -1, and I need to do -2 as well. For lambda equals -1, I'm going to look at a plus I. I don't have a anymore, so let me use my sheet. That was -1 plus 1, so that would be 0. 7 minus 1, 0, 2, 0, and 0, 15. I have -2 plus 1, -1. All right. So this I've reduced already. We'll reduce to this. Again, at this point, you should be getting a free variable. If you're not getting a free variable, that means either you have the wrong eigenvalue or you've reduced badly. All right, so in this case, we do have a free variable. X is free. So my eigenspace will be x is s, y is 0, z is 0. So I get x, y, z is 1, 0, 0, s. So that's going to be what I take as my one element basis. So basis of e minus 1 is going to be 1, 0, 0. That's what I get for lambda equals to -1. The final one was -2, I think. Yeah, -2. So I'm going to look at a minus -2i, and a was -1, so I get 1, 0, 3, 0, 0, 15, 0. Oh, let me get the reduction before I put this down. The reduction will be 1, 0, minus 1, 0, 1, 0, 0, 0, 0. Again, I have a free variable. And so we get x is s, y is 0, and z is s. So my eigenspace looks like this. I'm going to use that vector as a basis for it. So my basis for e minus 2 will be 1, 0, 1. At this point, I have 3 different eigenvectors that form basis for each of the eigenspace. If I put them together, they'll automatically be linearly independent because the different eigenspace are independent. All right, so I have my P. I'm just going to put these 3. So I'm going to take P to be P1, P2, P3. P3 is still on the board, so let's use that. 1, 0, 1. P2, I don't remember. P2 was 1, 0, 0, and P1 was 1, was it 1/5 I took? So here, I don't remember what I did. It's either 1/5, 1/5, 1, or 1, 1, 5. I think I did 1/5. And then D will have the eigenvalues on the diagonal. And so that means the eigenvalues of 1, 0, 1 is -2. The eigenvalue of 1, 0, 0 was -1. And the eigenvalue of, let me double check, and then that was 1. All right, and what we've done shows that D is P inverse AP. Just a note, if you don't like fractions, you don't have to use 1/5, 1/5, 1. You could take any basis. You could multiply. You could choose a better. You could choose 1, 1, 5 as the generator of that eigenspace, and then you'd get this P right here. The D would be the same. The D would be the same. All right, so that's it for A. Now in B, I'm asked to compute powers of D. It was D to the 10. All right, so D is pretty simple as a matrix. I want to see what happens when I compute powers of it. So let's start with D squared. D squared would be 1, 0, 0, 0, minus 1, 0, 0, 0, minus 2, times exactly the same matrix. And so I'll get 1, 0, 0. I'll get 0, 1, 0, 0, 0, 4. Let me write it here. If I take D cubed, that would be 1, 0, 0, 0, 1, 0, 0, 0, 4. Actually, let's do D. Well, I guess it doesn't matter. Times 1, 0, 0, 0, minus 1, 0, 0, 0, minus 2. And I'll get 1, 0, 0, 0, minus 1, 0, 0, 0, minus 8. All right, so at this point, I want you to see a pattern. I don't want to compute all these powers. In fact, if I was actually going to compute all these powers, I would probably compute D4, then D8, and multiply D8 by D2. But at this point, I want you to see that because it's a diagonal matrix, all these powers are particularly nice. I'll just take the diagonal entries and put them to the power n. So d to the 10 is minus 1 to the 10. Sorry, that's plus 1 to the 10, minus 1 to the 10, 0, 0, 0, minus 2 to the 10. So I'll get 2, 4, 8, 16, 32, 64, 128, 256, 512, 1024. So that's D to the 10. Alright, so diagonal matrices have really nice powers. You just take the powers of the diagonal entries.